Hello, welcome. In this short video, let us look at a graphical representation or graphical interpretation of the convolution integral. So, we are going to look at a graphical interpretation of convolution integral. Specifically, we are going to look at the different intervals of doing convolution integral. So, how do we solve this convolution integral for different values of the time t? So, that is the main question we want to answer. So, given a signal x of t that has a structure defined within a window of length t, that is assuming that it starts at 0 and stops at capital T, that is a given input x of t, and then we have the impulse response h of t that has a similar structure within the window, that has a similar structure that within a window from 0 to a. Here we are assuming that t is less than a. So in this case, we want to find the convolution of these two sequence or these two signals x of t and h of t. So for that purpose, we have to basically solve the formula y of t or derive the basically apply the formula y of t is equal to integral x of tau h of t minus tau d tau. So this is our x of tau. Now we have to reverse and shift the h of tau. So it must be, this is our h of minus tau. Now our goal is to find the value of this integral and the limits of the integral for various values of the time t. So in this case, we will make the assumptions that t is always less than a, and then we are assuming that x of tau is the fixed signal and h of t minus tau is the one that is being reversed and shifted. So we can compare this signal x of tau to a station that is usually fixed, and then our h of t minus tau to a moving train. So in the first interval 1, the value t is less than 0. So x of tau will look like same, that is x of tau has the same shape, but our h of t minus tau will look like following. So this is from 0 to t, and this is t and t minus a. Here we have t is less than 0, that is the interval. So there is no overlap. So basically y of t is equal to 0 for t less than 0 because there is no overlap. So we can compare this interval 1, our first signal that is x of tau is like a station that is fixed, and our h of t minus tau is like a train that is approaching the station, and then the front end of the train, that is the nose of the train, has not reached the station. So there is no overlap. So the train is still approaching the station. So that means the overlap is 0. Now let us consider the second interval. So in the second interval, interval 2, the value of time t is between 0 and capital T. In this case, the signals will look like the following. So this is 0 to t, or x of tau, and this is our h of t minus tau, and t is between 0 and t. So obviously t is here, and then we have t minus a here. So the t is between 0 and capital T. Here the overlapping region is basically from 0 to small t. So that is the overlapping region. So the integral should be from 0 to t d tau, and here we will have x of tau and h of t minus tau. So the limits are basically from 0 to t. So in this interval, we can clearly see that the train has actually arrived at the station, but it is still running. So the nose has actually entered the station. So that means there is some overlap between the train and the station. There is a partial overlap. That is, it is from the left side of the station. So that is interval 2. It's like train entering the station. So the integration is from the starting of the station to the end of the train, or the basically h of t minus tau. So the limits are from 0 to t. Now consider interval 3. In this case, so previous interval, the value is from 0 to t, that is t is from 0 to capital T. So in the third interval 3, that is in interval 3, the limits are from t to small a, that is the value of small t time is between t and a. We are assuming capital T is less than a. So in that case, the signals will look like following. So the signal x of tau is from 0 to t, x of tau, and h of t minus tau is again from t minus a to t. Here we are assuming t is greater than t, but it is less than a. So that means there is a complete overlap. So the integration is from 0 to t. So y of t will be equal to integral 0 to t or h of tau, x of tau into h of t minus tau d tau. So that is the value of the signal in this interval from capital T to A. So in terms of the train and stations, this is interval 3. The train is at the station, it is basically stationary. So we have a complete overlap, that is the whole station is usually covered, and that means the overlapping region is from the starting to ending of the station, or in other words x of tau. So that's why the integration limits are 0 to t. Now let us move on to next interval. So in this case, interval 4, the value of time is between a and t plus a. That is, t is greater than a and but less than t plus a. So in this case, the signals will have the following structure. So this is 0, that is t, this is t minus a, that is t, and this is our x of tau, this is our h of t minus tau. So when you look at this the station and the train, so we can clearly see that the train is leaving the station, so only the back end of the train is within the station or within the boundaries of the station. So the overlapping region is from the back end of the train to the front end of the station. So the overlapping region is from t minus a to t. So y of t will be equal to integral t minus a to capital T and x of tau into h of t minus tau d tau. So that is the overlapping region. So this is the overlapping. So this is the overlapping region, t minus a to capital T. So that is our y of t for this interval. That means it's basically like a train leaving the station. Now let us move on to the last interval, interval 5. So in this case, our time t is greater than t plus a. Here it is t is less than t plus a, so we cross that value also. So t is greater than t plus a. In other words, the train has left the station. Even the back end of the train is outside the boundaries of the station. So in that case, there will not be any overlap. So in terms of the signals, 0, t and t minus a. So t minus a is greater than t, or in other words, t is greater than t plus a. So no overlap. That means y of t will be equal to 0 in this fifth interval. So that means the train has already left the station. So to summarize, in this video we have looked at the graphical interpretation of the convolution integral. Specifically, we are looking at the different integration intervals of a convolution of a continuous signals. So given two signals are basically x of t and h of t, we basically fix one of the signals, usually the smaller one, and then we move reverse and move the other signal, say h of t. So we have x of tau and h of minus tau. So usually t is less than small a. Now to find the convolution integrals, we have to consider the following intervals. So in the interval 1, we assume that time is less than 0. In this case, x of tau is fixed and its limits are 0 to t, and then h of t minus tau, it starts at t minus a and stops at t, and this t value is less than 0. So that means it is like a train approaching a station. It's like a train before entering the station. So the front end of the train is has not crossed the boundaries of the station, or it has not entered the station. So there is no overlap between the train and the station, or in other words, there is no overlap between x of tau and h of t minus tau. So that means y of t is 0 in this interval. In the second interval, the value of t is between 0 and capital T. In other words, the train has entered the station. So only the front end of the train is within the boundaries of the station. So in this case, there will be some overlap, and the overlap is from the beginning of the station to the starting point of the train. So in other words, it is from 0 to t, assuming t is the starting point of the h of t minus, t is like the right side boundary of h of t minus tau. So the interval is from 0 to t. So y of t will be equal to integral 0 to t x of tau h of t minus tau d tau. And in the third interval, the value of time t is between capital T and A. In other words, the train is at the station. The train is at the station. So the whole station is covered by the train. So the limits of integration will be the boundaries of the station or the smaller signal. So that means the limits are from 0 to t. So y of t will be integration from 0 to t, x of tau, h of t minus tau, d tau. So that is interval number 3. Now in the next interval, the value t, small t, is between a and capital T plus a. So that means in terms of the trains, the train has started to leave the station. So there is a partial overlap from the right side. So that means the back end of the train is still within the boundaries of the station. So the integration limits are from the back end of the train to the front end of the station, or in other words, it is from t minus a to capital T. So y of t will be that integration from t minus a to capital T. And in the final interval, the small t is greater than t plus a. In other words, the train has left the station. The train has crossed the boundaries of the station. So there is no overlap between the train and the station. So that means there is no overlap between x of tau and h of t minus tau. So there is no overlap. That means the integration is 0. So y of t is 0 in this interval. Thus we can compare a continuous convolution integral, that is a convolution integral for continuous signals, to basically a train and a station, that is different stages of the train and with respect to the station, and then easily understand the limits of the integration for different values of the time t, or different intervals of the time t. Thanks for watching.